In this chapter, I will discuss functions. There are two basic types of functions, those that are predefined by the C compiler and those that are defined by the programmer. Regardless of the type of function, functions serve three main purposes in a program. First, functions make problem solving easier by allowing programmers to break large and complex problems into small and more manageable tasks. Second, functions speed up program writing by allowing programmers to use existing code to perform common tasks. Third, because functions can be used as many times as necessary in a program, the programmer does not have to duplicate the code in different parts of the program. Demo 7 is a sample program which uses a programmer-defined function. A programmer-defined function can be either a value-returning function or a void function. This one is a void function. A void function is a function that does not return a value. It simply performs a task. You may want to use a void function in a program to display information such as a title or column headings, something which does not require a calculation. In this sample program, a void function is being used to simply display a line in the output. Every function has three basic types. First, there is a function prototype. In this case, the function prototype is labeled void display line. Display line is the name of the function. Notice the parentheses, which indicates this is a function, but there's nothing inside of the parentheses. That's because nothing is being passed to this function. In order for a function to operate properly, it must have a prototype defined before it is called. Scrolling down in the program, you'll notice that there is a statement that simply says display line, followed by the parentheses. It also ends in a semicolon. This is the calling statement. This is how you tell C to use the function which has now been defined. And below the main function, you'll notice the programmer-defined function definition. In this section of the program, you tell C exactly what you want this function to do. In this case, all we want the function to do is to display a line of dashes across the screen, and then cause an inline to occur. And that's it. That's the purpose of this function. Notice the contents of this function is enclosed within the braces. I'll compile this program to observe its execution. It compiles normally, and then when executed, and I enter a number such as 9, you'll notice the row of dashes that is displayed. That is because the function was called to display this row of dashes after the user input and before the result of the calculations is displayed. The calculations themselves are rather simple. The square of the number is simply taking the number entered and multiplying it by itself, and half of the number is simply dividing that number by 2. As you can see, these calculations are performing correctly. Now, in reality, if all you wanted to do was display one row of dashes across the screen, then going to the trouble of creating a function might not be worthwhile. But if, however, we want to call this function multiple times, we can now do so by simply calling that function wherever we want it to be displayed. For example, if I would like that line to be displayed after the title result of calculations, I can simply call that function by typing display line and calling that function. If I also wanted to have that below the last line, I could do so. The point is that now we have a function that we can use multiple times. I only need one function prototype at the top, and I only need the function itself defined once. I can now just call this function each time by simply naming it. We'll recompile this program and then observe the run. I'll type in a 5 this time, and now notice the row of dashes have been displayed in each instance that I called it. I will use the program we used in the previous segment to discuss in detail each of the three components of a function. First, you must declare a function prototype. In our example, the function prototype is simply void display line. A function prototype is in essence declaring the function to C. If the programmer-defined function is located after the main function of the program, the program will have one function prototype for each function definition in that section. You usually place the function prototypes at the beginning of the program, after the include directive, such as in the example that you see. If you compare the function prototype to the syntax of the function header, you'll notice that the syntax is almost identical. The only difference is that the function prototype ends in a semicolon, whereas the function header does not. In this example, the display line function did not require any information to be passed to it. In most programs, however, you may need to pass information to a function in order for the function to perform its task. We will discuss passing information to functions very soon. Moving to the calling statement in the program, which actually we have 3 of, and you notice that each one is identical. To call or invoke a programmer-defined function, you simply use its name and any arguments that you may need to pass. Once again, in our case, we're not passing any arguments. This calling statement requires no arguments. It simply is display line, open and close parentheses, followed by a semicolon. When C processes this statement in the current program, it temporarily leaves the main function in order to process the instructions in the display line function. C will process the statements within this display line function in the order in which they are entered in the function. In this case, the function statements will display the row of hyphens first, and then advance the cursor to the next line. When C encounters the display line's function's closing brace, it marks the end of the function. C will then return to the statement immediately following the one that called the function, in this case, the cout statement. The third component of a function is the function definition. The function definition starts with a function header. Note the syntax of this carefully. The keyword void is followed by the name of the function. You'll notice that the function header does not end in a semicolon because it is not considered a C statement. The function header for a void function begins with the keyword void, which tells the C compiler that the function does not return a value. You follow the void keyword with the name of the function. The rules for naming programmer-defined functions are the same as for naming variables. To make your programs more self-documenting and easier to understand, you should use meaningful function names that describe the task that the function is to perform. In this program, for example, the name of the function displayLine indicates that the function is simply to be used to display a line. You will notice that a set of parentheses and an optional parameter list follow the function's name in the syntax. Not every function requires information to be passed to it, so not every function will have parameters listed in its function header. Our displayLine function in this program is an example of a function that does not have a parameter list. Functions that do not require a parameter list will have an empty set of parentheses after the function's name. The opening and closing brace marks the contents of the function. The displayLine function in this program contains 2 statements. The first statement displays the row of hyphens, and the second advances the cursor to the next line. I will now use our sample program and modify it to create and call an additional function. I first will need to create a prototype for my function. This will be a void function, and the purpose of this function is to calculate the results. So I've created a function prototype. The calling statement will go in place of the current statements that are causing the actual calculation. So I will call this by simply using the name of the function, calculate results. And for the time being, I will simply leave it as the open parentheses. The third component is, of course, to create a function definition. So I'll go below at the very bottom of the program and create this function definition. I have created a shell of sorts for this calculate results. Rather than retyping this code, I can simply cut and paste the calculations that I want. The calculations are in the main program. So I will cut these to remove them from the main function and place them into my function definition that I've now created. Now, the only difference to this program is that the placement of the calculations have been removed outside of the main function and into this programmer-defined calculate results function. Now, our next task will be to compile this program to see if it actually works. I'll warn you now that there is a problem with this program. We click on Build. You'll notice that the compiler tells me that 3 errors have been generated. If we scroll up to the top one, in fact, you will see that each one of these error messages refer to undeclared identifier. And the identifiers in question are number squared, number input, and number halved. If I double click, it's taking me to the statement that I cut from the main function and placed into this programmer-defined function. The problem here has to do with the scope of the variable themselves. The way I've modified this program is these variables are outside of the main function. The definition of these variables, however, remain in the main function. And this is the problem. C could not recognize the variables since they are declared outside of the main function, or since they're being used outside the main function. A variable scope indicates which portions of the program can use the variable. The scope, which can either be local or global, is determined by where you declare the variable in the program. Variables which are called local variables are declared in a statement block, which is simply a group of instructions enclosed in braces. Global variables, on the other hand, are declared outside of any function in the program. Unlike a local variable, which can be used only by the function or the block in which it's declared, a global variable can be used by any statement that follows this declaration in the program. You should, however, avoid using global variables. If more than one function needs access to the same variable, which is the case in our example, it is better to create a local variable in one of the functions and then pass that variable only to the other functions that need it. And this is what we'll do to correct our program. Since my function requires the use of number squared, number input, and number halved, when I call this function, I need to pass these variables to it. So, returning to the calling statement, I will insert inside the parentheses the variables that I wish to pass to this function. I have typed number input, number squared, and number halved, separated by commas, inside the parentheses. Now when this statement is called, or this calling statement is executed, these 3 variables get passed to this function. Now there's one more piece of business that needs to be taken care of, and that is that the function definition needs to accept these variables. So I need to include in parentheses these variables so that they will be accepted into this function. In the function header, you must declare the type of variable that's being passed to it. In our case, all variables are float. So I'll simply type float, the name of the variable, separated by a comma, and then I do likewise for the remaining 2 variables. Again, preceding each with the keyword float. And of course, make sure that you're spelling the variables in a consistent manner. Now that we've changed our function header, we also need to change the function prototype. Our function prototype currently simply says there is a function called calculate results, but the prototype does not have the information that C needs in order to process this data that's being passed to it. You do not need to tell C the exact variables, but you do need to tell it what type of variables to expect. In this case, we are passing to it 3 float variables. So we simply need to type float 3 times to represent that each variable that's being passed to this function will be of type float. Let's compile our program to see where we stand. As you can see, it returns no errors, no warnings. We'll now run our program. Once again, I'll enter a number. I'll enter the number 7. As you can see, the program is run, but our answers are now 0. There is one additional modification we need to make to this program, and I will demonstrate this in the next segment. You'll recall from the previous segment that we had this program that is compiling normally. I'll recompile it, and is executing, except when I enter a number such as 9, the results are simply coming back as 0. The problem here is the scope of our variables. You'll recall that we created a function prototype to pass and to accept 3 float variables. Our calling statement is passing 3 variables, number input, number squared, and number halved, and our calculate results function header is accepting these 3 variables. Once the calculations take place, then the answers of our calculations are then being stored, or displayed rather, in the main function. And this is where the zeros are coming from. The calculations are taking place, but yet when they are received back to the main function, they are retain the value 0. And this is why. We are passing these variables by value. Variables can be passed either by value or by reference. When you pass a variable by value, C passes only the contents of the variable. So when these 3 variables are passed to the calling statement, they are being passed by values and not by reference. What does this really mean? When you pass a variable by value, C passes only the contents of the variable to the receiving function. The receiving function does not have access to the variable in memory, so it cannot change the variable's contents. You pass a variable by value when the receiving function needs to know only the value stored inside the variable, but the receiving function does not need to change the value stored in the variable. You can also pass a variable by reference. When you pass a variable by reference, C passes the variable's address. In other words, its location in memory. The internal memory of a computer is like a large post office, where each memory cell, like each post office box, has a unique address. Because the variable's address, or location, is passed to the receiving function, the contents of the variable can be changed by the receiving function. To pass a variable by reference in C, you must include the ampersand, which is called the address of operator, before the corresponding formal parameter's name in the receiving function's parameter list. The address of operator tells the C compiler to pass the variable's address rather than its contents. You pass a variable by reference when the receiving function needs to change the contents of the variable, which is what needs to take place in our example program. Nothing needs to be changed in our calling statement. What needs to change is in our function prototype and also in the function header. Since the 2 variables that need to be changed are number squared and number halved, we need to place the ampersand after the word float in the second and third parameters respectively. It is important to place these in a one-to-one relationship. That is, this float refers to number input. Number input does not need to change, so therefore we are not using the address of operator. Number squared, however, does need to change. So in the function prototype, I'm including the address of operator. Likewise, for number halved, I've included the address of operator. Now, we need to do this to the function header in addition to the function prototype. So scrolling down to the function header, you'll note the actual names of the variables. The syntax requires the ampersand, or the address of operator, to precede the name of the variable in both cases. So I'll place the address of operator in front of the variable name that we want allow to change. Now let's recompile our program to see where we stand. Now it compiles normally, and we'll run the program. I'll enter the number 9, and as you can see, our program is again working correctly. As far as the user is concerned, the program functions in the exact same manner as our original program, except now we're making use of functions. You might wonder, well, why to use functions? Why not just use the calculations directly into the main function? And in this particular sample, that might make perfect sense. But as programs become more complex, it becomes useful to create these so-called functions to allow to be called multiple times. And the result in this example, we're only calling this one time. But I could call this function several times, and I can in fact pass different values to it each time. The more complex your C programs become, the more useful functions will become.